Okay, good afternoon, everybody. Today I have the privilege of talking to you about the Intrepid mission concept. Our overarching goal is to unravel 4 billion years of lunar magmatism by traversing across one of the most geologically diverse regions of the moon. Our diverse science objectives include determining the origin of the Procellorum creep terrain, testing large-scale mantle overturn hypothesis, understanding the nature of the Rhina Gamma magnetic anomaly, and the fate of the core dynamo over time, and many other key lunar science questions. But I'm letting my natural geologic enthusiasm get ahead of me, I think. And we'll just plow ahead and come back to the science objectives in a moment. Okay, first, briefly throw the slide up here of the Intrepid team. We have a very dedicated and experienced proposal team, which you see on the left column and halfway down the right column. And we've been working with the JPL, Punch Mission Concept Studies team, which has been really a delight. There's too many people to mention the names of, but they've challenged us and made our mission concept much better. And they've come up with an awesome implementation, which I will briefly touch upon. Okay, here's a CAD-CAM of the Rover design as it is today. We definitely come in at the New Frontiers class mission. It's designed for operation in day and night conditions. The range of greater than 1,800 kilometers. Depends on a high level of autonomy. The lifetime is greater than 4 years. It's capable of slopes up to 15 degrees, four-wheel drive, four-wheel steering, a 60-centimeter ground clearance, 5 degrees of freedom robotic arm, and it's powered by a 300-watt next-gen RTG, and the fully margined mass is 415 kilograms, including the 30 kilograms of science payload. The JPL team also came up with a solar-powered version, but it cannot move at night, and there are other limitations, and so it requires 3 extra years of operation to come up with the same science return. Okay, we've broken our overarching science goal of unraveling 4 billion years of lunar magmatism into 3 themes with very detailed questions beneath those. We'll start out with the evolution of the lunar interior over 4 billion years. And this, to get to the end game here, requires diversity of ages and compositions, wide variety of ages and compositions. We want to look at the composition of basaltic volcanism through time, heterogeneity, and evolution of the mantle of shallow. And when did volcanism end on the moon? Looking at primitive composition of the mantle from pyroclastics, looking at the nature and extent of non-Mare volcanism, nature of a Procellorum creep terrain, and the decline of the core dynamo and magnetic field over time. We also are going to investigate the diversity of styles of magmatism, flood basalt placement and associated rills, vents, flows, and tubes, origin and composition of cones, domes, and shields, pyroclastic volcanic processes, differences in composition and physical properties. And key goal is finding and characterizing intrusive bodies and their relation to effusive deposits. And finally, our third theme is what happens to these materials after they're replaced. And we'll be looking at the nature of crater impact formation, holistic sedimentation, ray formation, and physical properties of the regolith outward from the impact. Target material dependence of crater characteristics and impact mechanics by traveling over a wide variety of geologic materials, and the variations in the space weathering across a wide variety of terrains and ages. And specifically, what is the relationship to the radiation environment, hydrogen abundance, and magnetic anomalies. All of our science here is responsive to the current decadal, and we really hope it's going to guide the next decadal. That's our key goal. With this study. Okay, we'll basically talk about the measurement overview, and then we'll talk about the instruments. We want to characterize the mineralogy and petrology at the level of anthracite, olivine, orthopyroxene, binopyroxene, ilmenite, and glass. Look at key elemental abundances, both major and minor chemistry. Characterize the magnetic environment, strength, orientation, polarity. We'll be doing this over meter spatial scales. Look at variations in crustal density as we traverse across these very geologic terrains. Measure solar wind charged and neutral particles as a function of time of day, local magnetic anomalies. Characterize the radiation environment, probe the regolith structure, estimate the depth of the regolith, discontinuities, document grain size, shape, and color, and look at the geotechnical properties. Estimate maturity of the regolith, what is its relative age, using a couple of optical techniques, and characterize landforms, what are the shape of flow forms, crater forms, vents, etc. And one point I'd like to make is that it's not just the science that we're collecting at the stops, but we are collecting science data as we're traversing across the moon. There we go. So we're measuring as we traverse across the moon. Another important aspect of the mission is that we get the third dimension by going up to the edges of craters and measuring material that was ejected from depth. It's now sitting on the rim, so it's drill holes provided by Mother Nature. Okay, here's our instrument suite. We're going to be measuring galactic and solar cosmic rays with RMAS, body fixed pointing up, a magnetometer, a gamma ray neutron spectrometer, a TriCam, which is a suite of black and white telescopic FarCam and stereo RGB imager, and then a point spectrometer that borrows the optics of FarCam, and the hand lens imager, and all of these optical instruments share the same electronics box inside the rover. And then alpha particle X-ray spectrometer, again, to look at elemental abundance. Electrostatic analyzer to characterize the solar wind, and a passive laser retroreflector to allow measurements of the location of the rover from an orbital laser. The power and mass instruments are all from high TRL instruments, except the point spectrometer. I already mentioned that those optical instruments share the same box inside the rover, which really simplifies the rover design. Our total mass of the payload is 17.1 kilograms, and our power is about 30 watts. Okay, concept of operation. CLPS Lander delivers the rover to the moon. The rover regresses the lander, initiates checkout, and starts operating. Rover travels to investigation sites along predetermined traverse. Autonomous operations between the sites and at investigation sites. I cannot emphasize too much the importance of autonomy. And we can pre-plan these traverses because we have meter scale imaging from the beginning to the end of the traverse. And in key areas, 2 to 4 meter per pixel digital terrain models, which really allow us to make realistic traverses in terms of power usage and hazard avoidance. The focus in investigation sites will typically spend 12 to 48 hours during the day, longer at night. Health and safety data is transmitted while the rover is moving. Science data is transmitted at a high rate while the rover is stationary. The rover progresses and takes measurements during the 2 weeks of sunlight. Rovers typically traveling 500 meters per hour over sustained distances autonomously. Sometimes when we're in steeper or rougher terrain, that may drop down to 100 meters per hour. There's continuous science operations while we're roving with the gamma ray neutron spectrometer, the magnetometer, electrostatic analyzer, and RMAS. Every 10 minutes, we acquire a point spectra and a set of images to document what we've been driving over. And that works out to about every 80 meters, longer distances at lower speeds. We stop every 4 hours, which is about 2 kilometers, for 1 hour to document the traverse and get a long integration with the APXS. This is known as an interval stop. During periods of darkness, the rover traverse progress is limited, but that doesn't mean we're not working. So here at night, we focus on long integration measurements and downlinking our science data. There's limited movement in terms of speed. Probably our maximum speed at night would be about 50 meters per hour and perhaps 2 kilometers over a night cycle. But even though the distances are short, we're placing the instruments on key targets to get long integrations, both with the gamma ray neutron spectrometer and the APXS. Rover stops, as I mentioned earlier, are all pre-planned, taking into account science and traversability and time of day. The current mission design includes 131 major and 981 minor sites over 3 Earth years. We have 1 year margin built in, which gives us a total mission of 4 years, and the traverse is 1,800 plus kilometers. The mission requires a high degree of rover autonomy, and it's a new way of thinking about rover operations. Get the measurements and continue on. Okay, I'll walk you through the 6 legs of our traverse here to give you a feel for the science that we're going to collect in the terrain we're going to cross. We land just south of the Rounded Gamma formation. We traverse across with 30 major stops, 131 interval stops over a distance of 259 kilometers over 6 lunations. We take multiple passes across the swirl, as you can see here, measuring the magnetic environment and the space environment. The materials here that we cross in this part of the traverse have ages estimated between 3.3 and 3.5 billion years. We will measure the mare composition as a function of depth through crater radio traverses, as I mentioned earlier. And as everywhere, look at regolith development on different materials and crater mechanics. We will, at each one of these traverses, the red text at the bottom is what the team thought was a great science highlight for that section of the traverse. But by no means is the only science result that will come out of that part of the traverse. So here we're going to, the knowledge we gain in the magnetic field orientation, strength, and spatial variation will discriminate between the dike, metal-rich impactor, basin ejecta, and cometary hypothesis for the origin of the magnetic anomaly. Now we'll go, after we're done at Rounded Gamma, we will traverse through the Marius Hills, which is one of the most unusual volcanic terrains on the moon. It has over 100 domes and cones. There's nowhere else on the moon this variety of volcanic edify. There's 31 major stops, 290 interval stops. Total distance is 608 kilometers, and that's 10 lunations. We're going, as we traverse across this terrain, we'll be searching for intrusive bodies, characterizing the magnetic environment, the space environment interaction with the surface, which is a little bit of what I said earlier at Rounded Gamma, but the Rounded Gamma tail extends into the Marius Hills, so we'll continue that study. We're going to look at the nature of domes, cones, rills, vents, tubes, and pyroclastic materials, possibly discover non-Mare volcanism. The age of the materials in here is not all that well known because of the complexity of the geology and the topography, but age estimates between 2.5 and 3.3 billion years. We'll look at the Mare composition of a function of depth and along the length of flows. And one of my favorites here is we'll test hypotheses for causes of variations in volcanic morphologies by looking at the composition, volatile content, and the fusion rate which tells us much about the evolution of the mantle source regions, particularly combined with the results from the other 5 segments. Okay, the Oceanus Procellorum traverse, there's 24 major stops, 196 interval stops for a distance of 405 kilometers, and we will cover this distance in 7 lunations. We start out at Mare materials that are 1.9 billion years old, and then end up at 1.2 billion. Of course, we don't know for sure the age dates, but these are from crater size frequency distribution estimates. We'll be definitely measuring the radiogenic contents of the basalts because this is an area of PKT. We're not really sure whether the basalts are creepy or whether there's just creepy highlands material or intrusive material thrown on top. We will be studying one of the few shield volcanoes on the moon. We'll be looking for intrusive bodies beneath that shield and, of course, anywhere else along the traverse. Looking at ray mixing systematics, Mare composition as a function of depth, and the regolith and cratering mechanics. So again, a couple favorite results will be to measure the Aristarchus ray composition to test ray formation hypotheses. As you can see in the traverse here, we are definitely crossing over areas of rays, but also areas that are shadowed from the rays, so we can get a real good idea on how much mixing, how much local material is a ray, and how much ejected material. And we're also looking at how remnant magnetism declined through time, well, which is really an indicator of the evolution of the core dynamo decline. Was it rapid or slow? Will we even see remnant magnetism in 1.9 or 1.2 billion year old basalts? And then we transition into Aristarchus Plateau, a very popular site for planetary missions. There's been discovery proposals. There's actually a site for Apollo missions that never happened. One of the largest pyroclastic deposits on the moon. The age is not all that well constrained, but it's thought to be about 2.5 billion years old. We'll be examining the physical state and composition as distance from the vent, and also vertically, again, through radial traverses from impact craters that have punched through or into the blanket. We're going to be examining a supersized rill and vent. And it's actually a double nested rill, as you can see in this picture here, where there's a rill within the rill to look at the mechanics of rill formation. We'll be searching for intrusive bodies, maybe finding some evidence of non-Mare volcanism. And again, regolith development on a different type of material and cratering mechanics. So highlight of our science return here is to determine the composition of the pyroclastic deposit, which has really important implications for mantle heterogeneity and evolution, and its resource potential of the volcanic blast deposit should certainly not be overlooked. Okay, now, Aristarchus Crater. 20 major stops, 171 interval stops, 182 kilometers in length, 6 lunations. Topographically, this is one of our most challenging, well, it is our most challenging traverse. So our speeds of the rover will be about half of it there on the rest of the traverse. We'll be skirting around the southeast rim of the 45-kilometer diameter Copernican crater. Been age dated at about 200 million years. It's a hot spot, the hot spot of the Procellorum creep train. So we will be traversing over materials that were ejected from deep inside the crater, and the crater is over 4 kilometers deep. See along here in these color differences, this is a wide-angle camera, UV visible color stretch. So we're going to get the full suite of materials exposed in that beautiful central peak at the bottom of the crater. Really get at, what is the creep train? And it's amazing how we still don't really know what the creep train is to this day, but we will solve it with Intrepid. So we're going to test the hypothesis that Aristarchus Crater excavated a silicic volcanic complex, or maybe some other completely unknown ancient crustal material. and test basaltic underplating as a mechanism for tertiary crust formation, two of our favorites from this section of the traverse. Then we head north towards our smallest target and our shortest traverse, which is the Aristarchus Irregular Mare Patch. It's 2 major stops, 4 interval stops, 5 kilometers, and 1 lunation. The sun is coming from the left in this picture. That's an impact crater, not a bubble. And this is part of a class of deposits that were first identified from Apollo data, but the extent and number has expanded out from a couple to more than 50 with the advent of LRO data. And it's very controversial, the origin of the imps. There's one school of thought that they are very young volcanism, something on the order of less than 100 million years, which goes against the paradigm of the lunar mantle shutting off eruptions about 1 to 1.5 billion years ago, to another hypothesis that they were actually formed as very long ago, 3.5 billion years ago, with magmatic properties that are very unusual that result in misleading crater counts. And we will easily test this hypothesis by traversing across the contact between the imp and the Aristarchus Crater ejecta, because the imp appears to be superimposed on the ejecta. So if we can show that the imp is younger than the ejecta, then clearly at least that imp is not 3.5 billion years old, but it's 200 million years or less. So that was somewhat of a slam dunk result at the end of our traverse. As I mentioned earlier, all stops are pre-planned. They have different time periods, sometimes 12 hours, sometimes 48 hours, sometimes 24 hours. This is just an example of a typical 48-hour stop. Okay, we arrive, we'll continue integrating with the gamma neutron spectrometer. We immediately take a FARCAN 2x2 mosaic to document and aid in placement of the APXS. The bar, this is real time here at the stop, 0 to 48 hours. The bar just doesn't show up in this swim lane chart, but trust me, it's there. And at the end, you can just barely see it showing up over there. Okay, next we acquire the TriCam observations, color stereo, and a FARCAM distant mosaic. Rotate the arm to position the APXS, integrate with the APXS. Then we move the APXS 3 more times in front of the rover without moving the rover. So we put it down to the left, a left position, then a near center position, and another near center position, and then off to the right. So we can get multiple measurements of the same, the regolith approach the rover at the stop. Then we stow the arm, prepare to depart, and we leave. And this is really a new paradigm for rover operations. The lunar night is your friend. There's nothing to be afraid of the lunar night. You're taking advantage of the lunar night. You get lots of measurements. Long distance roving is your friend. Again, there's no reason to be afraid of long distance roving. It's a way to get a very robust data set that addresses core questions. Autonomy is the key to long distance roving, and also to getting the measurements and moving on. And pre-planning the traverse and observations ensures maximum science return. So here's an example of one of the cones we're going to be visiting on our traverse at night. I'll walk you through a typical night stop. We drive to the furthest point at a night stop. As soon as we get there, laying down tracks, because over the course of the night, we're going to follow back on those tracks, ensure we have a good navigation landmarks. And by following the strategy, all we need is Hershines. We don't need any fancy headlights or spotlights or laser systems so that we can actually move safely in the dark. We first arrive at 14.9 solar time. You can think of that as the equivalent of 3 p.m. Take a black and white telephoto panorama inside the cone, stereo color panorama, a point spectrometer mosaic, 48-hour integration with the GRNS. Then we drive 50 meters, the sun sets, do another 48-hour integration, and then we move 50 meters 5 times, and we do it over again. We keep doing that, moving, so we're getting a full suite of measurements over multiple locations to really avoid the problem of wondering if the measurement is anomalous or truly representative of that particular terrain. We move again. Now we're on the lip, and then we move 100 meters to get on the outside flank. Again, integrating 48 hours, collecting other measurements. Then in our final position here, the sun rises. Take a large black and white telephoto mosaic of the cone and surrounding areas. And then we depart when the solar incidence angle is greater than is 10 degrees above the horizon, avoiding driving into large shadows. Again, here's the cone we're going to be visiting. I should have mentioned that that picture is about 1,600 meters wide, the grid facing at 152 meters. Okay, I'm not going to go, this is a really busy slide, but this is just to show you the amount of work we put into this traverse. For all of these 131 focus investigation sites, we came up with a library of modes to operate in, and different sites require different modes. We have these swim lane charts for each stop of what we're doing to really document the whole traverse, which is core information for getting a requirement down for the rover design. Okay, a quick summary of our stops and measurements. Focus investigation stops, there's 131 of them. Of those 131 focus investigation stops, 35 of them are overnight stops. We have 981 interval stops. There's greater than 1,800 kilometer of integration noodles. Again, remember, as we're driving across the moon, we're collecting this valuable science data on this continuous roving observations. And you can slice and dice those data as appropriate once we start analyzing on the ground. For example, calcium, which is a difficult to measure element with the gamma ray spectrometer, you might have a much longer binning in terms of the noodle than iron, and also depending on your science goals. So our total number of focus investigation and interval observations, with APXS, there's 2013, HLI 2103, point spectrometer 60, well, let's just call it 70,000, bar cam 48,000, color stereo pairs 35,000. Those are perhaps overly precise numbers, but I left them there because it illustrates the detail that we've gone through in terms of planning out the con-op so we can make sure we design the right rover. So while we're driving, we collect 31,000 observations. Those would be point spectrometer spectrum and lossy grayscale stereo pair documents the location of each PS. Those are critically important observations also for documenting change over time or change over distance on the traverse. So our total science data is 1.1 terabytes with 2 terabytes of available science downlinks. We have lots of margin for downlink, which will allow us to collect even more science data, which we have plenty of time to do, and some really totally awesome EPO movies and pictures. So this detailed inventory of observations is critical to power computing and downlink allocations, as well as documenting the data efficiency. In other words, will we be able to answer the questions that we are asking? And the answer is yes. Okay, here's a science return timeline. Some of our key questions on the left-hand side. The take-home message from this slide is that some of the science questions require measurements over the whole traverse, and others are quick returns from just that one segment, that one traverse. And sometimes we can supplement our, where the X's are, even though we've completed with the green. The light green indicates we're collecting measurements towards that goal. The dark green indicates we've got enough measurements to complete that goal. But sometimes we can do an enhanced science by continuing measuring similar or even different materials. Okay, next slide. So then you ask the question, why an 1,800 kilometer traverse? Well, the current traverse is the shortest route to interrogate 4 billion years of magmatic materials in place via a broad range of mechanisms, which is incredibly important to the science questions that we're asking here. We need this full time spectrum to begin a holistic understanding of lunar magmatism. And it's really a key to unraveling the formation and evolution of the moon, and to some large degree of the Earth-Moon system, and the early evolution of differentiated silicate bodies in general. And I would argue that this is a very small distance to traverse 4 billion years of lunar magmatism. And that's really, it's just the same distance as Phoenix to Houston, which was going to be my punchline when we gave this talk at LPSC. But now we're doing it differently, but it still doesn't change the fact that it's not, you shouldn't be scared of that traverse. And the technology is here today. So I say the time is now. And with that, I'll close and say thank you very much for your attention.
Great, thank you, Mark. We do have a couple of questions for you. Let's see, the first one from Michael Mishna at JPL. Is there time or a plan for accommodating any opportunistic science based on discoveries made at any of the individual stops?
Yes, there is some time built in to the traverse, but not a lot. And we have a whole year of reserve time. So if there's some amazing discovery that's made, we could certainly add a lunation here and there. Particularly as we get further and further into the traverse, I certainly wouldn't want to use up all my margin on the Reiner Gamma traverse. I really want to emphasize that the paradigm for Intrepid is really understanding the science questions and the measurements needed to address them, and building the rover and selecting the payload to get those data based on our current knowledge of the moon. Will certainly be unexpected discoveries. I mean, without doubt, that always happens. We will do our best to follow up on them, but we will not change the goals and objectives of the mission, unless, of course, we find an obelisk or something along those lines. Right? So that we are very focused to get the answers to these decadal level questions. So we can't be sidetracked with changing the mission halfway through. So that's my answer.
Great. And then on the other end of that spectrum, Jayadev Pradipra would like to know, what is the proposed plan of action once the predetermined traverse is completed? If there's still mission lifetime after that, where would you go next?
Oh, Rice and Domes. Can you
sure, great.
My screen. What we do is, and this continues our investigation of many of our core questions, and would be totally awesome as you traverse through more complicated Mare basaltic terrain. Here we head over to a hotspot in the PKT and up to the Gruheisen Domes, which are silicic, now known to be large silicic volcanoes from the fantastic data collected by Diviner. And then we'll get to go up into a highlands terrain that's a PKT hotspot. And now we'll have 2 traverses of highlands material that are PKT, and more Mare that we don't know if these are really creepy basalts or they're just contaminated basalts. So we have a very awesome potential for an extended mission, although I know I'm not allowed to talk about an extended mission. But this is our thought of what we could do. We're still in great shape at the end of this period. And as you can see, this would be a 1-year or 18-month addition to get from there to there based on the traverse that we've been making. And this is all very benign terrain. So long answer to a short question.
That's great. You know, just because you can't talk about it doesn't mean you shouldn't be thinking about it.
Yeah.
One more question so far. Let's see. The Michael I from last would like to know, does the calibration change during the 1,800 kilometer traverse, and is that making the measurements more difficult?
Calibration. Well, rather non-specific question, so I'll just answer in a generic sense. I guess the instruments will react to the lunar environment and change. We will have the ability to take a target along with us for some of the instruments, but not all. But that's always been, a key part of a science team to monitor and calibrate the instrument using the in-flight, so-called in-flight data as you traverse along. A lot of our measurements, key philosophy, our science here is to get the measurement from 2 instruments rather than just one. Barbara mentioned that in her talk, and it's a good setup. The APXS and the gamma ray neutron spectrometer really complement each other. They are measuring to the 80% level the same same elemental suite, but they also have differences in that the APXS looks at the top few centimeters, and the GRNS looks down through 20, 30, 40 centimeters. So we will compare those instruments where it's appropriate to see when they're, but we will be relying on the fact that in key science areas, the measurements might be different.